Good afternoon, everybody. Here is my marker. Here it is.
Afternoon, sir.
Afternoon, sir.
Right. 1 second. All right, guys. So we're finished with polynomials. With respect to the teaching of polynomials, we're moving on to the next topic. And that is what you will find with pure maths and odd maths. Don't spend a lot of time on the topics. Two topics that you might spend a lot of time on is like trigonometry. And my brother only topic that requires a good amount of time. Differentiation and integration, yes, but you really don't need a lot of time even on those. For pure maths, we're gonna spend some time doing the odd maths part, odd maths level, differentiation and so on. Same thing with the tricks. The Tuesday, Friday, and I want to move it to another level in the Sunday program. When we start the Sunday program. All right. So today the topic is Surds, logs, and indices. And Surds, logs, and indices is similar to polynomials in that it is on the odd math syllabus. It's also on the pure math syllabus. The Surds, logs, and indices that they set in odd maths, very, very basic. And they just step it up a little bit for pure maths. Not even much. They don't step it up much. There's one identity that they add to the list of identities that you must know. Right? And I show you. And they also use log to this ln. ln function is a log function. Look at the calculator, it's a log, log to base 10, but it also ln, log to base E is a number like pi has a value, E has a value, right? You have log to this. And then all the rules that apply to logs, they apply to logs with any base. All the rules that apply to logs with any base. We're not going to touch on the logs yet. We're going to touch on the surds first. All right, so let me just go to the notes. As I said, I have a must-know sheet for you. I'll send that must-know sheet to you soon, so that you know you have the important and critical things that you all need to know. All right, with these topics, surds, logs, and indices, in particular with the logs and indices, the logs and the indices, it don't make no sense if you're going to do a logs and indices question without knowing the rules and the laws. They have some laws of logs, laws of indices. You have to know the laws. You have to know the laws as presented from left to right and also from right to left. What do I mean by that? I'm not sure what I mean by that, right off the bat. What I mean by that when I say right to left, left to right. So for example, the log of a product, the log to base, any base of a product, so PQ, is equal to the log of P to the same base plus the log of Q to the same base. You have to know and use this law from right to left in some questions, and you have to know the law from left to right. From left to right and from right to left. You have to know the laws both ways. What happens to some people is that they study the law this way, and if they give them something like this, they have a problem coming here. You have to learn all the laws both directions. Same thing with indices. So for example, with indices, if you know, for example, that x squared to the y is equal to, multiply these is equal to x to the 2y. You have to know that you can go this way, but that depending on the question that you're doing. I can interchange these and put y here and squared well, that way up here. Y here and squared there. So it might be convenient for you to go from this, if you have that, to write it like that, depending on what you do. So you have to learn the laws, both directions. I'm going to present it, or you will see them in a book. So you have to know that you have to learn the laws and you have to be able to use them interchangeably. From left to right, from right to left, depending on what you're doing with the system. All right? All right. But let's talk about surds first. What are surds? A surd is an irrational number that is expressed in that form, square root of a number. And what does the word irrational mean? Everybody know what the word irrational means? What's an irrational number? So 0.25, is that irrational? No, it's not irrational. Because 0.25 is 1 over 4, which is not a ratio. Right? So an irrational number is a number that cannot be expressed as a ratio, having a whole number numerator and a whole number denominator. That's what an irrational number is. A number that cannot be expressed as a fraction, cannot be expressed as a fraction, having a whole number numerator and a whole number denominator. The only number that is an exception is any number divided by 0. They can't divide by 0. Good? But that is not a real number. So any number that can be expressed as a fraction with a whole number numerator and a whole number denominator is rational. Any number that cannot be expressed like that is irrational. Understand? Irrational. Now, pi is actually an irrational number. Just that there's a close estimate to pi, which is 22 over 7. But 22 over 7 is just an approximation of the value of pi to a certain number of decimal places. But pi actually is an irrational number. So you can know an irrational number when it is expressed as a decimal. The values do not repeat, and also it is non-ending. So it's a non-ending decimal. When you express a rational number, an irrational number in decimal form, it is non-ending. The number of decimal points go on forever. It's non-ending. And secondly, the values do not repeat. There's no repeat of the value. So for example, if I write 1.3333333, these are repeating, don't it? So that can be that's a rational number because the decimal place values are repeated. So then that is actually 1 over 3. You get me? So if the values repeat, then it is a rational number. So most irrational numbers that we're gonna work with in surds are the ones that are expressed like that. And we're not talking about the square root of 4. But the square root of 4 is equal to 2. So square root of 4 is not a surd. Square root of 3 is a surd. Because if you calculate the square root of 3 in a calculator and look at the values, you will see that it is non-ending. So whatever the maximum number of decimal places that your calculator can show, it will fill them out. And the values are non-repeating. The values are non-repeating. The square root of 3 cannot be expressed as a fraction having a whole number numerator and denominator. And therefore, most times, these surds are left as they are. So instead of trying to write it as a decimal, it is more accurate to just leave it as the square root of 3, and the square root of 2, and the square root of 5, and the square root of 7. Values like this. It's just better to just leave them in the surds form. All right, so everything I've said so far is actually on the slide. All right, it's on the slide. So people online, okay? And following?
Yes, sir.
All right, good.
Sorry, kind of low.
I'm
The volume kind of
low.
low. Yes, sir.
Right? I can't speak any louder than this, believe me. So you need to turn up your device. I don't have any control over the volume. Here, I'm speaking loudly, believe me, as I normally do. Right? And I'm right over the device, right over the tablet that I'm using. All right, so you just need to other persons having the same experience that I'm sounding low. I'm sounding low to you, Kai.
No.
Okay, so you see it's your device. You say by saying we are low, it's your device. Because this is how I normally operate. All right, so let's go. All right, so those are examples of surds: square root of 2, square root of 7, square root of 5, square root of 3 are examples of surds which have no exact value. They are irrational and are often expressed as they are. They will define rational number already. So they are irrational because they cannot express as fractions with a whole number numerator and a whole number denominator. Square root of 4, square root of 16, and square root of 25 are not considered surds because those can be worked out into exact values. Square root of 4, you know, is 2, square root of 16 is 4, square root of 25 is 5. So these are examples of exact values. They are rational because when you work this out, and it equals 2, 2 is the same as 2 over 1. Right? So you are able to express 2 as a fraction by putting it over 1. And therefore, it is not an irrational number. It is not a surd. Right? So these are not referred to as surds. Only the ones that are not exact and cannot be expressed as a fraction. So irrational. So the square root of 4, that's some little things to know. If I give you a question and I give you this in it, you cannot go and drop one plus or minus on it. It is taken to mean the positive square root of 4. See? Positive square root of 4. You can't go automatic, you can't go randomly drop a negative on it. So if the root square root of 4 appears in an expression, you have to just take it to mean the square root of positive square root of 4. Alright? That is it. Alright? So if I tell you that x is equal to the square root of 4, then it means that x is equal to 2. Don't put no plus or minus on it. Alright? But if you have that x squared equals 4, and you know have to produce the solution for this. You know have to produce the solution for this. Then it means that x can now be plus or minus 2. Because it means that from here, the x becomes plus or minus the square root of 4. That's how now you introduce the plus or minus. All right? But if they give you this in a question, you have to take it as a positive. All right? So I'm saying that because people do that sometimes. Right? Take the plus or minus and you're not solving to find the value. All right. Operations with surds. What are some of the things that we need to do with surds? Some basic things. Multiply them, divide them, add them, subtract them. And there's one particular one that everybody has to know, which is to rationalize the denominator or rationalize surds wherever they are. So in advanced level, we tend to have to rationalize surds on the denominator of expressions. Because what happens is that when you have a surd or you have a value, you normally want the denominator to be a rational number, right? Most times. But pure math students, you're going to experience situations where you have to rationalize the surd that is even in the numerator for the benefit of what you're doing. Especially when we start to do limits and continuity, and in particular, differentiating from first principles. There's some differentiation from first principles where you will have to rationalize a surd even while it is in the numerator. And as I mean, you have to rationalize it where it is. And we'll see that. The first one is simplifying. Just that does some operation. And this is more advanced. And sometimes pure math students have to apply some of these as well. So the square root of 50, what you do, you look for the perfect square in 50. It's 25. You're looking for the perfect square in 50. And so you express the 50 as 2 times 25, like that. Or 25 times 2. And then that now is equal to the square root of 25 times the square root of 2. And the square root of 25 is 5. And so we have simplified that. So sometimes you're doing a question, for example, and you just say you must prove this, prove that something works down to this, and this is where you end up. You have to be able to simplify it down to that. Now, a lot of your calculators will be able to do this for you, go from this to this. Right? Your calculator will be able to do it for you. But a lot of the time they want to say work. You get me? Or your calculator can do that for you. Right? Alright. That is our first simple one. Then we have to be able to multiply surds. So one of the things we have to understand in multiplying surds is that, for example, the square root of A times the square root of A becomes equal to A. Right? Because the square root of A right here is the same as A to the half. Square root of A right here is A to the half. And when you multiply indices, you add the 4. Half and half is 1, so it becomes A to the 1, which is A. Alright? So we have to know this one. Square root of a number times square root of a same thing equals that. Right? You have to know that. So that's an example of something that we might have to do. Let me bring up something over here and let's work it out instead of put it on the slide. Work it out over here. Step by step. So if you have that thing to do, I will see on the screen there, which is 3 plus 2 root 5 times 2 minus 3 root 5. We expand this to normal way. It is this times each of them. And then this times each of them. Good? So some people set it up is that they say you use this times this and this times this, and then this times this and that times that. Same thing, right? Same thing. So if we multiply by this first times each of them, then we're going to get 3 times 2 is 6. Then 3 times this, not the negative, becomes negative 9 root 5. We'll go to this now. Then this times this is plus 4 root 5. And we'll do this times this now. So first thing, the sign is going to be negative. Then we're going to have the 3 times the 2 is 6. And then the root 5 times the root 5 is 5. But I can appreciate that. But I go to that. And then you consolidate the values. Consolidate the values. So this becomes equal to this right here says 30, right? It's minus 30. So this is really 6 minus 30 is negative 24. So it's negative 24. And then now these two is negative 9 root 5 plus 4 root 5. So it becomes negative 5 root 5. But I go to that. All right, so look at the slide. It's the same thing there. Simplify all the way down. Get the same thing right here. All right, easy stuff. Simple operation. Everybody must be able to do search. People who had math before should be having an easy time right here. So some revision. All right. So, I mean, these things very easy, but we still have to go through them, right? We have to go through them. We have advanced people here, we have pre-advanced people here. People who are advanced already, good. People, a lot of us just doing advanced for the first time. So, these things really very easy. Even though people get them wrong still. All right, let's continue. Rationalizing the denominator. This is the one that you will more likely be asked to do on an exam paper. As I said, do it about it as well, because you have calculator that can do these things for you. So you can check. All right. This is a process of removing surds from the denominator of a fraction using the following. That's the first thing that I showed. Product of roots, product of surds, this can get rid of the root, right? And this now is what we call conjugate pairs. Conjugate pairs. They multiply conjugate pairs, they become the difference of two squares, and that is how you can eliminate surds. So let me show you over here now. That is some simple examples to show you. Or you rationalize a surd. What you have to do to rationalize a surd. So if I have 2 minus root 3, right? If I multiply 2 minus root 3 by its conjugate, what is its conjugate? Its conjugate is when you have the same values, but this sign is between them is different. It's the opposite sign. If I multiply this by its conjugate, I'll put it in red, which is 2 plus root 3, then I have set up the difference of 2 squares. And that's the method we use to rationalize surds. So it becomes this squared minus this square, because that's the difference of 2 squares. But recognize that difference of 2 squares, right? So this really becomes 2 squared minus root 3 squared, which then becomes 4 minus 3, which then becomes 1. All right? So how do we apply this? Let's look at an example of how we apply this. Suppose then that same expression was on the denominator of a fraction. And let's say on the numerator we had 2 plus root 3 instead. And we want to rationalize the denominator. Right now the denominator is irrational because it has the surd in it. We want the denominator to become a rational number. Then what you have to do to get the denominator to become rational, you have to multiply it by its conjugate, which is 2 plus root 3. But because you multiply the denominator by 2 plus root 3, you have to multiply the numerator by the same thing, which is 2 plus root 3. And then under here now, this calculation under there will rationalize the denominator for you. You got wow. Oh, the computer cut off in the part. Oh, that's connection order. Let me check if I'm still on here. Alright, so we're back. People online are back. People online are back. Can you see the screen?
Yes, sir.
Yes, sir.
Alright. We just had a dip in the data. Alright, so I didn't see this calculation. So I said, let me do it again. Let's do it again. So I'm saying, let's say you get this fraction right here. And they want you to leave the denominator rational, because right now it is irrational because of the surds that's a part of it. And so this expression, it has a rational part and an irrational part. So together, it is an irrational number. All right? So to make the denominator become rational, you need to get the surds from under it. So a method to do that is to multiply it by its conjugate and set up the difference of 2 squares. So we're going to multiply the denominator first by the conjugate, which is 2 plus the square root of 3. But we can multiply the denominator by 2 plus the square root of 3, and multiply the numerator by the exact same thing, which is 2 plus the square root of 3. And then we'll look at the product on the denominator. It is the difference of 2 squares So this becomes equal to 2 squared minus root 3 squared. And the numerator becomes 2 plus root 3 all squared. Right? So if we continue to solve, the numerator expand on the perfect square now becomes 2 squared is 4, then twice the product of the 2. Twice the product of 2 means that we multiply these two things, we get 2 root 3 and we double that. So we're going to get plus 4 root 3. And then the second term squared is a 3. When squared is root 3, we're going to get a 3. And the denominator now simply becomes 2 squared, which is 4 minus root 3 squared, which is 2. Right? And so this would work out to 7 plus 4 root 3 over 1. Now we don't need to show the 1 here, but you will get a rational number in the denominator. All right, so that's a typical thing to do. Rationalizing. This comes a lot on the multiple choice about odd math and pure math. The funny thing about it, is that you can use a calculator, so it's really very weird how to set these things and multiple choice papers. All right. So if we continue with the slide. So you see these are conjugates, the only difference between them. So that's an A, that's an A. This is B root C, and this is B root C. So the difference between them is that this is a plus, that's a minus. So that they are the difference of 2 squares. All right. So you end up getting that, which reduces to that. That becomes rational. All right. So that's the method that we're going to be using. Again, that's the same thing again. Right? They are conjugates. That's the only difference between these two rational numbers is that you have this is a plus, that's a minus. So if you proceed, they are the difference of 2 squares, that's what they get. That becomes A minus, that's a square right here. It's a square. That's not clear, but it's a square. That's a square. And we'll clean up this slide. So it becomes A minus C. Alright? So those are some simple things you have to do with surds. Difference of 2 squares. Alright, so another example, this one. You multiply the denominator by root 3. That was a root 3 times root 3 will give you root 3, right? So that's it. Multiply the numerator and the denominator by root 3. That's what we did here. And it becomes that. That one, that's similar to one that we did a while ago. Multiply the denominator first by the conjugate of the denominator, then multiply the numerator by the exact same thing. This is it. So here is what I'm multiplied by. This I'm multiplying by this right, which is the conjugate of the denominator. Alright, and you proceed as I did in the example a while ago. And the denominator becomes rational. You know, to become to the left in this example. Alright. Alright, so let's move on. We'll see these in some examples later. We just want to get to the notes and then we can get to the example. We really want to get the logs and indices. Comes under one topic. So it's logs and indices. No, don't the logs. Alright, indices now. Indices now. That is pretty much what you'll be doing with Surds. You just need to practice doing those things. Eh? Simplifying, rationalizing, multiplying, dividing. All right? Laws of indices. All right. Let's have some C6 for me. Yeah? So the expression 5 to the expression 5 to the 4th power. The 5 is the base and the 4 is the 4 or the index, right? So those are terminals that you know. First law, that to multiply indices with the same base, you add the 4. You have to know these laws. I can also give them to you, learn them and apply them. I'm going to show you how you use them in some examples. But the key thing I was saying to you earlier is that you have to learn these laws this way and also that way. You have to learn them both ways. Right? You have to learn the laws both ways. But there are questions where you just have to break them up. I want to see those later. Right? For example, you have this, you have to break it up into that, for whatever reason. You want to see them in some examples later. That's the first law. There's a little proof there, but it's really irrelevant. Just learn the law. You just have to learn the law. Right? When you multiply numbers with the same base, you add the powers. Alright, and that is C6 form. Alright, that's the first one. Second one, when you divide, you subtract the powers. When you divide numbers with the same base, you subtract the powers. When you divide numbers with the same base, you subtract the powers. Again, there's a little proof there. I'm not going to spend any time on that. Something to know is that any number raised to the power 0 is 1. Anything raised to the power 0 is 1. And this now, this rule, this law is a spin-off from that law. It's actually a spin-off from that law. And it is right here. It is right here. Because if you have n to the fourth power, n to the fourth power, if you have n to the fourth power divided by n to the fourth power, this law says must subtract the powers, right? So it becomes n to the 4 minus 4. And then 4 minus 4 becomes n to the 0. We all know that n to the 4 divided by itself equals 1. See that? That kind of proves it, right? So this is the end of it. So this is all you need to know. Any number raised to the power 0 equals 1. So this is easy to know. Any number raised to the power 0 is 1. All right? Then we have the reciprocal. Negative power means that you move it. You move it on either side of this division line. There's a name for this thing, I just don't remember. I just don't remember. There's a name for that line. I just don't remember. Right? So this equals 1 over n to the p, but you can go the other way as well. Meaning, if I have, for example, 2p to the minus 1, like that, it is the same as 2 over p. Right? Right? The minus means the move on the other side of the division line. Right? And if I have 2 over p to the minus 1, if I have 2 over p to the minus 1, I can bring it up here and put p. So this now will be equal to 2p. You know what, right? So once you move it, you put on the minus sign. Let's put another way. If I have 2p, I can write 2p as 2 over p to the minus 1. Understand? So once you move it, the sign of the power changes. The power is 1 right now. If you move it above or below the division line, the sign of the power changes. Right? The sign of the power changes. Right? So you have to know all those ways. And this is again a little proof of this law. This right here. This right here is a little proof of that law. This is a little proof of it. Look at it. It proves this. Right? When you get the negative power, it ends up being that, right? All right. So again, I don't really care about the proof. You just need to learn the laws, right? You have to learn the laws. You have to know them. So there's a summary pH in there. This one again is one that you have to know. When you raise that indices to a higher power, you multiply the powers. And you have to learn the law both ways. So it means that this, for example, see this? This can become equal to n to the q raised to the power of p as well. Realize that? It can become n to the q raised to the power of p. So I can switch around these. And there are questions you have to switch them around. So for example, if I'm doing a question and I have 2 to the x squared, it might be convenient based on what I'm doing to write it as 2 squared to the x, because they are the same thing. And then I realized that it's actually 40 days. Get me? It's actually 40 days. So it might be convenient sometimes to switch these around depending on what you do. And there are some budgets where you have to do that. Right? Manipulate it. So you have to learn these laws left to right and from right to left, as we have said. This again is like a proof. Not gonna care too much about the proof. Right? Let's move on. You have to learn the laws and use them. Then we have when your power is a fraction. So this is one that we have to focus on again. When your power is a fraction, the numerator is your power and the denominator is your root. Alright? So like right here, we have 1 over r. It becomes r. Let me write it to this. If I have n to the 1 over r, n to the 1 over r, this is the same as n to the 1. The 1 is the power and the r is the root. The r is the root. So that's why I have this. I don't need to show the 1. Alright? Let me use another example. Look at this one. Let me write over here. Look at that thing that's up here. Let me write over here. Let me write over here. What is that? Just on the slide. These are things that you absolutely must know. So if you have a number raised to a power and a root, the numerator, this is the power to which you raise the number, and this is the root that you take of the number. Alright? So then this expression really becomes equal to and again, every time the phone rings, that's what happens. Yeah, every time the phone rings, that's what happens. All right, guys, let's hold on. So you say this when I wrote this. All right, guys. Sorry about that. Every time the phone rings, I just cut out the hotspot because I'm using hotspot. All right. So do we understand this, everybody? R is the root, P is a power. You can take the root first, as is the case here, and then the power second, or you can raise to the power first and then take the root afterwards. It doesn't matter, it's the same difference. People online can say that they understand it.
Yes, sir.
All right. I'm going to do these things with numbers too. So it's the same thing that I have here that is on the slide over there. Same thing. So P is a power, R is root. Let me use some numbers as an example. So for example, I have 8 to the 2/3. And 8 to the 2/3. Normally you take the root first, because the root cannot break it down first, right? So you build it back up. So this is the same as the cube root of 8 squared. Because this is the root and this is the power that you're raising. The cube root of 8 inside is 2. So this really becomes 2 squared. And then the 2 squared is 4. The answer is 4. You could do the other way around. You could raise it up first and write it then as the cube root of 8 squared. Cube root of 8 squared. The 8 squared is 64. So it becomes the cube root of 64. And the cube root of 64 is still 4. Right? So that is it. So you could have gone that way as well. All right. Let's continue. Summary. So this is the page that you need to know everything. So this is the page that you need to screenshot and study. Plus, it's going to be an emotional sheet. This is the page that has everything on it that you must know. This page right here. That's the first one, multiplication. Second one is division. Third one is a raise to higher power. These are the 3 that you get in add maths. Right? Add maths. Then you have to deal with the root one. And that is the power one. All right, let me write over on this so you can see. So this is 1 over r right here. So, all right here is a p. All right this is a p. This is a p. All right, so those are the things that they must know. They are the most know sheet. I said the most know sheet. There's some other stuff we spoke about. Here, like any number raised to the power 0 is 1. I will introduce the negative power. When the power is negative, it can move below the division line and change the sign of the power. I move above the division line and change the sign of the power, right? And then we can use the negative also means reciprocal. The negative power also means reciprocal. Right? So we can use the negative power right here to flip this, flip the A and the B. The negative power also means reciprocal. All right. So these are best results when all expressions are expressed in the same base. Once you're doing an question with law, with indices, you want everything to be expressed in the same base. Right? So if you get something like this is simplified. I mean, this probably cannot make sense to me. The character can do it, but just for illustration purposes, all these values can be expressed to base 2. Right? So it cannot make sense to express everything to base 2. This actually right here is a cube. Right here is a cube. 2 cube. There's 2, the 4 is 2 squared, and then you put back the cube. All right. Yes, again. And then you add the powers and the numerator by the same base, and then you apply the power law on the denominator. And then you want to subtract. When you divide numbers with the same base, you subtract. So these are all basic stuff. Everybody must know this already. Anybody would add maths? If you go with this, those are doing add maths for the first time. Yeah. To be able to deal with this. All right. Come to love now, guys. That is Surds, Indices. We're just focusing on the laws and stuff, and we're going to jump onto some questions after we finish. That's how I approach it at this level. Go to the notes, and then when we finish, we'll just attack questions. All right? And practice questions and do past papers and stuff. So what is our log? Log of a number. Log of a number is equal to a power. Add math people, doing add math for the first time. It's something you have to know. The log of a number is equal to a power. What that does, it creates a connection between logs and indices, because indices have to do with powers. Numbers raised to powers. The log of a number to a base is raised to a power, 1 power. You know, the power to which the base is raised to be equal to the number. So this statement really creates the connection between logs and indices. This statement creates a connection between logs and indices. So this is, you know, this is what I just said on the first line. The log of a number is equal to a power. And I deliberately use n for number, p for base, p for power to illustrate this, right? So a log is always to a base. Because remember it connects logs and indices are connected. The logs and indices have three things operating in that all the time. You have a base, you have a power, and they work out to a number. Right? And these three things in any number are connected either this way or that way. And they go, if you notice this is a double side, a two-way arrow, two-way imply. So basically what I'm saying is that this implies that, and this implies that. And there are questions that you'll be doing questions. There are situations where you'll be doing questions. I have to simplify it down to something looking like this, and then you can move to that and then solve. Especially logs equation. To simplify them down to something looking like that, and then you convert it to this, and then you solve. Most of the questions in logs that you have to solve. That's what you have to do. There's another approach that we can use, and I'll show you. Right? A lot of the times you have a logs equation, some complicated log expression, and you want to solve. You bring it down to something simple like this, and then you're able to write that. All right. So look at it carefully now, guys. N is a number, B is a base, P is a power. The log of this number to this base is equal to this power. That's what we say. So that number, this number, is equal to this base raised to this power. The number is equal to the base raised to the power. All right? And we can put values to this and prove it to be true. All right? We can put values to this and prove it to be true. So let's look at the log of 25 to base 5. Log of 25 to base 5 is equal to 2. Why? Because the number 25 is equal to the base of 5 raised to the power 2. See there? The base of 5 raised to the power 2. That's a relationship. They're looking for number, base, power. Number, base, power. The log of a number is equal to a power. What power? The power to which the base is raised to be equal to the number. You can understand that? Especially people doing this for the first time. You can understand it? So this is what is in yellow that is key. Appreciate and understand. When you calculate the log of a number, you actually calculate in a power. What power are you calculating? You're trying to find the power to which you have to raise the base that you take in the log to. It's a log to base 2, log to base 10, log to base 5. You're trying to find the power. You take log of a number. You're trying to find the log of a number is going to give you the power to which you would have to raise the base for that result to be equal to the number. And that's why I deliberately use the letters N, B, and E for you to see the connection between logs and indices. Because indices, you have a base, that's a base, that's a power, and this is a number. Same thing in this expression. You're taking the log of a number to a base, and I'm telling you now that when you take the log of a number, it is equal to a power. That's why we start out with this line up here, so you can understand. And when you calculate the log of a number, you're finding a power. What power are you finding? You're finding the power to which you have to raise the base to be equal to the number. Or the power to which the base is raised to be equal to the number. All right? See here again. Log of 3 to base 9 is equal to a half. Why is that? Because you have to raise 9 to the power half in order to get 3. Because 9 to the power half is equal to 3. 9 is a base, half is a power, 3 is a number. So number 3 is equal to base 9 raised to power half. Right? That's what it is. Remember, you have to be able to go both ways. So you have this one, you have this one, indices, you have to be able to go that way. You can show the relationship that way as well. So for example, 8 is the same as 2 cubed. Means that the log of 8 to base 2 is equal to the power 3. Because in this relationship, right here, this is your base, this is your power, and this is your number. So this is your number, this is your base, and you get your power. If you log of a number, you get your power. Right? So the number base power thing that you're looking for. What is the number? What is the power? What is the base? Base power number. Base power number expressed as logs here. Base power number expressed as indices. You can interchange between them. Base power number. Base power number. The log of a number to a base is equal to a power. The number is equal to that same base raised to that power that it is. Alright? That's what this is. Alright. We practice these things, will become like second nature, right? So 8 to 1, same as 3 to the 4th power. 3 is the base, 4 is the power, 81 is the number. So it means that 81 to base 3 is equal to power 4. So looking for base power number, base power number, base power number. Alright? Alright, so there are certain things that you must know. Positive base raised to a power will always produce a positive result. So 4 to the 4 squared is 16, which is positive. But 4 to the minus 2 is also a positive value, 1 over 60, but still positive. Alright? So remember now, the power can be positive or negative. The base is positive. The number will also therefore be positive. So when you raise a positive number to a power, it must come out back to be a positive number. Alright? And so there are some conclusion that can be drawn from this. This is it. The n must be positive. The n, what we're saying here is that the n must be positive, right? In both cases, this is the n, that is the n. And the positive. A number, watch this now, a positive number, any positive number raised to any power can never be equal to 0. Right? And let me put base. Any base raised to a power can never be 0 unless the base is 0, but we don't find log to be 0. There's always log to be some value. We don't find log to be 0. So what are we saying here, so in that in the log relationship, the n can never be 0. The n always must be greater than 0. It can't be 0 and it can't be negative. You can't find the log of 0 and you can't find the log of a negative number either. If you're solving a question, doing a question, and say you're solving for the n, and you get 0 as an answer, you can't accept it. If you get negative as an answer, you can't accept it. I'm going to see examples like this. Right? So if you're doing a question and the answer will cause you to find the log of a negative number, you cannot accept that answer. If you're doing a logs question and solving a logs question, and the answer that they get will cause you to be finding the log of a negative number, then that answer is not valid. You cannot find the log of 0, you cannot find the log of a negative number. But we're taking that the base is always positive. We're taking that the base is always positive. Alright? So that is what we are saying here. That's what we are saying here. So it cannot be 0, and it cannot be negative. So n can only be positive. We cannot find the log of a positive. Alright. What is it saying? It's often more convenient to convert from logs to indices in order to evaluate simple problem questions. There are some additional stuff. we'll use these when we're solving questions, right? So don't worry too much about this. So some of the hints. So don't worry about it. We're gonna show you the methods and the approach that we're gonna use to solve our questions. So don't worry about this too much. Right? Don't worry about this too much. Don't worry about this too much. Because you see this can work out with a calculator like this. Right? And you have to get the calculator that can work out. So don't worry about this too much. All right. Laws now. Now, on the slide, we have like some proof of the laws, but it's really not important. So again, I'm just gonna go to where we are listing the laws. You have to know them. It's only about 5 or 6 laws, 3 main ones, and then some spin-off from them. Right? Here must have one additional law that you must know and use that advanced won't get, and I show you. Right? And you have to learn the laws and practice with them to know them. And you have to know them from left to right and from right to left. You cannot do a logs question unless you know the laws. You don't make no sense to say, boy, you do the topic of laws. I don't know the laws. The first thing you must know are the laws. From left to right and right to left. Because if you see a question, you're going to just don't know how to move. Because the questions are centered around the use of the laws. Once you say a logs question, you have to use the laws to simplify it, to solve it, to do what you have to do with it. So you're going to do a logs question if you don't know the laws. Right? So the first objective of learning the topic of laws, same as indices, is to know the laws. Right? They're not going to ask you to prove them. They're going to ask you to use them. They're going to give you questions for you to use the laws. All right? So you know, make no sense to talk no more about that. You have to learn the laws. Have them on your fingertips. As you see a question, you see a setup for the laws, you must know which law to apply. Learn the laws from left to right, from right to left. And even though in this example, and here now we're dealing with maybe log to base 10, for example. The same laws work for log to any base. Same laws. Once the base is the same, and these laws are set up for when the base is the same. There's a change of base law that I'm going to show you. But generally speaking, the laws are derived from when the base is the same. We're not going to prove. We're going to list them down and go through them, and I want to do questions and use them. All right. So the proof is there. I'm going to put the law in the yellow. So that's the first law. Law of a product becomes the log of the sum of the values to the same base. The first law. Law of a product becomes the log of the sum of the numbers to the same base. And the spin-off from indices. From the first law of indices, the spin-off from the law of indices. So look at it. So here, you can add that. So here, the log of this product becomes the log of m plus, as a product becomes plus the log of m. And the base is the same. That's the first one. Then the second one is division. Second one. Log of a quotient, subtract it. The log of the base m of m over n, because the log of m minus the log of n. The same base. Advanced students, you must know these laws. And as I said, you have to learn the laws from left to right and from right to left. You have to know the law from left to right and from right to left. Because I might be doing a question as this you have to use and go to that. Get me? Not all the time the question is going to be about going from this to that. A lot of the questions you'll have to go from this to this. All right? That's the second one. So the product one, the quotient one, we have the power one. The power one. Third one is the power one. See there? Now if a number raised to a power, the power can become the multiple, the front. The power comes to the front. Multiply. See? Like that. The 4 comes to the front and multiply. And this law stem off the first one. Stem off the first one. Okay, I'm sure it's not sure an example. What do the question is? What do the question is? Let's learn the law. Now, if a number raised to a power, the power comes to the front. I have to learn the law this way as well. They go from this to this. So in other words, if I have a multiplier on the log, I can bring it up on the power up here. Right? You have to learn the laws both ways. You have to learn the laws both ways and use them. Number 3. So basically, that covers what advanced students need to know in terms of the laws. Right? Those are the laws that advanced students must know and use. Number 4 is the change of base law now that pyramid students must know and use. Change of base law. Advanced won't get change of base law to use, but still a good law to know. Because sometimes you're doing a question and the change of base law might just help you to make it easier. And you cannot be penalized for advanced knowledge. You know something more than your syllabus. You can penalize it for knowing something more than your syllabus. Alright? Then we go down to the law, the final line of the law. This is it. And I'm going to write it over. It's the only one I'm going to write over here and show you how you set it up. All right, instead of just looking at the final. Watch this now. If you have the law of M to base B, this becomes the log of the M over the log of the B. And then change the base to any value I want, C. That is it. Change of base law. So you introduce a new base. Understand? So the log of this, over the log of this to the new base. Look at it. So that log of the number over the log of the base to a new base. Change of base law. Change of base law. Change of base law. Any new base you can give it. You can give it any new base. So for example, suppose you have a question, right? And the majority of the question is in log to base 2. We'll see our example or this plan. Suppose you're doing a question, you have log to base 2 of x plus log to base 2 of y equals, and you have another thing now, which is log to base 4 of x. So we get that to solve. You have 2 base 2 over here, so what is a log to base 4? It means that we need to change our one to base 2. Okay, you know, the laws that we have in the first 3 lines that you want to use to simplify expression, first 3. You want to bring everything to the same base. So I can put these 2 together using the first law, don't it? And this will become the log to base 2 of xy, don't it? And then this one now, I'm going to put log of x over log of 4, and then I put the 2 of them to base 2 now. See that? Then we have everything to base 2.
So what happens to the y?
Huh?
What happens to the y?
So we multiply it here, so that's the first log. The log of a sum equals the log of the product. First law, look over here and show you. First law. The first law here, first law. So this was we just applied a while ago, the first law. Just start going this way with the first law now. We're going this way. That's what we did. See that? See that, Chade?
Yes, sir.
Right. So you see, you have to know the law both ways. But this sum became this log of this product right here. And then I change this 2. And then this right just, that is just equal to 2, That's equal to 2. Why is it equal to 2? Because 4, remember now, log of a base to a 4 is equal to a power, don't it? So what power is this equal to? I have to raise 2 to the power 2 to get 4. See that? So the answer for that is 2. But another way you can know it is 2 is because this 4 is same as 2 squared. So what is now? Instead of 4, I'm going to change it to 2 squared right now. Where it is? 2 squared. And then what do we say? We say this 2 can come to the front, don't it? What is that? I'm going to put that at the front. We can put that at the front. And then log of 2 to base 2 is equal to what? Equal to 1. Log of a number to its own base is equal to 1. Why is that? Because 2 is equal to 2 to the 1. See that? 2 is equal to 2 to the 1. Remember, say this equal to power, you know. This thing equals a power, you know. This thing is equal to a power. The power to which you have to raise 2 to in order to get this. You have to raise 2 to the power 1 to get 2. But we also have a thing where we say the log of a number with its own base is equal to 1. Right? But this is an example of how you have to change the base. Right here. Right? How you have to change it. But let's continue. We're going to see examples later. The thing is, you're not going to see a lot of change of base questions, even pyramids. Not going to see a lot of them. Set them, but not a lot in pyramids. Set them, but not so much. Set them occasionally, but not so much. Believe me. But change of base law, very useful. All right. But there's an extension to the change of base law, which I'm going to call now. Let me just call it reciprocal. There's an extension to it. Watch it. Watch this. First, we have to understand that the log of any number with its own base is equal to 1. This is like something you have to know. Log of a number to its own base is equal to 1. The log of 10 to base 10 is 1. Log of 5 to base 5 is 1. Log of 2 to base 2 is 1. So watch this now. If we have the same log to base b of m, I'm talking about this over here. I'm gonna do an amendment to the change of base law. And I set it up how we said before, which is the log of m over the log of m. If I change the base to m and put m right here so and m right here so. No, I have a mistake. This is b. This is b. It's supposed to be b. Let me start over. Got a mistake. Let's go again. This starts out being the log of this, which is m, over the log of this, which is b, right? And then we need to put in a new base, right? Here and here, right? A new base. I'm saying I'm going to conveniently let that new base be m. I'm going to put m here, m here. I can put any new base, you know. I can put any new base you want. So this log of m to base m is equal to 1, don't it? So this then becomes 1 over the log of m to base b. So when you look at these two things carefully, look at these two things carefully. When I switch around the number, see that? We take the reciprocal. So this is for pure maths, you know. Pure maths students have to know that one too. Add maths won't get this. Pure maths will get it. So use some numbers like the log of 10 to base 3 is equal to the 1 of the log of 3 to base 10. Easy as that. Let's switch around the number and the base is the reciprocal. The change of base law as well. Very powerful when you use it. Understand? People online go to that, everybody okay? think I have it on the slide here as well, that thing. I have it on the slide, why? It's supposed to. All right, so I think I introduce this first. The log of a number to its own base is equal to 1. Log of a number to the same base is equal to 1. The log of 1 is 0, guys. Log of 1 to any base is 0. It's another thing you must know. The log of 1 to any base is 0. The log of 1 to any base is 0. Why is that? Why is that? Because any number raised to the power 0 is 1. So once the power is 0, the number is going to be 1. Don't it? Remember now, once the power is 0, log of a number is a power, you know. So once the power is going to be 0, the number is going to be 1. Because any number raised to the power 0 is 1. So log of 1 is 0. Log of 1 is 0. These are some things that you must know. It's another thing that you must know as well here. So it is very important. And this becomes very important for pure math students. The log of a fraction is negative. The log of a fraction is a negative value. Remember a fraction, a number that is less than 0. Remember, say the number has to be greater than 0. So I'm talking about the log of any value before you reach 1 is negative. The log of 0.5, the log of 0.2, the log of 0.25, the log of 0.9. All those values are negative. The log of a fraction value is negative. The log of a fraction is negative. I'm going to show you a question about that applicability. Very, very important. As simple as it looks, yes or no, it's very important, especially in some inequality logs system, logs inequality system. Very important. You have to know that the log of a fraction value is a negative number. You're not going to see the negative number, you have to know. You're going to see them in some questions. Pure math students must know that. Not that math students. That math students might have to work it out, but pure math students will get questions that test your knowledge of that. Log of a fraction value is negative. If you use a calculator and try log of any fraction value, log of 0.5, 0.8, 0.99999. Once you don't reach 1, and you can put any base you want. It's gonna come out to be negative. So that you must know. Let me just tell you how it's useful. Let me give you an example of how it's useful. Give you an example of how it's useful. Give you an example. Let's give you an example of how this becomes useful right now. All right, so I'm telling you, and I'm going to give you an example right now how this might be useful. Let's say I'm solving a question, right? And I get it all the way down to x times the log of 0.25. And let's say this is base 10. LG normally means base 10. And let's say that I have this as greater than 4. I'm going to try to solve that. Let's try to find x. The inequality. What you would more than likely think of doing is to just divide by the log of 0.5 on here. Don't it? So you might do this. X equal, not equal, greater than, x is greater than 4 over the log of 0.25. But this would be wrong. Why would that be wrong? Because you're dividing by a negative value, because this is negative. So you would have to know that the log of a fraction is negative. You understand that? Because the log of a fraction is negative, if you divide by the log of 0.25, you're divided by a negative number. We're not seeing it there. Right? With a negative number in the background, don't it? So you have to reverse the inequality sign, because when you multiply or divide with a negative number, you have to reverse the sign. So this sign would have to become less than this sign. We'll have to reverse. Why? Because the log of 0.25 is negative. You have to reverse the sign. To do this, you put it in red. To do this, reverse. Because The log of 0.25 is negative. And once you have an inequality, and you multiply or divide by a negative number, you have to reverse the sign. The log of 0.25 is negative. I don't know the value yet, but I must say negative because it's the log of a fraction. So pure math students, you must know that. All right, you must know that. So these things that are on the notes page, you must know. So if I continue over here, it's like a proof of it, but we don't worry about the proof, just know it. And then using the change of base law, we get the reciprocal thing again. See right down here, so that show you. The log of m to base t becomes equal to 1 over the log of b to base x. All right? This I just showed you. This is what I showed you earlier. All right? So you have to know that you can go from this straight over to that. Pure math students. Advanced students don't need to worry about that. Pure math students must know that and be able to use it. All right? Must know how to do that. That's for pure math. Change of base law. You have a summary page, everything on it. Which is why you really just want to know. Screenshot the summary page and study everything on it. First law. Remember, you have to know the laws from left to right and right to left. That's first law. That's the second one, the quotient one. The product one, the quotient one. I call this one the power one. The power one. You find the log of a number is to a power. The power comes to the front. You have a change of base. A pure math. So the first three is add maths now. I'm not sure the add maths. Them three, I'm mad add maths there. This is add maths. I'm mad add maths there. Right? So the fourth one is pure maths. Add maths not getting that. Change of base law is not an add maths syllabus. That also is pure maths. So add maths, I know everything in them, but pure maths only need to know the three. All right. Let's do this too. So I'm saying add maths must know these three. A. Add maths. Pure maths have to know everything. But add maths only need the first three. Alright? See to me. Now smile. That one add maths must know as well. This one. No marking. Add maths must know this one as well. But pure maths must know that. No, log of a number to its own base equal 1. Log of a number to its own base equal 1. So for example, if you get the log of x to base x, you know it says 1. Log of a to base a is 1. Alright? You expect you to know that it is 1. That's what this add maths must know. Remember what add maths things as we go. Pure maths must know everything. Add maths must know this as well. Log of 1 is 0, regardless of the base. The log of 1 is 0, regardless of the base. Any base. Log of a fraction is negative. I don't think that math students need to really know this one. But if you now get no inequalities with logs at maths level. Pure maths, yes. You can get inequality with logs. You have to know if you have to divide or multiply inequality by the log of a fractional value. Grade must tell you say you're divided by a negative, and you have to reverse the sign. Shade online, you understand that? And Kyle, Alex,
Yes, sir.
Who is online? Only two are online. What is done? Watching the class in the part. So, pure math students must know these things. All right, you have to have them in your head. There's add math things, few things you must know for add maths. Log of 0 does not exist. Log of a negative number does not exist. You cannot find log of a number that is greater than this. So just remember knowing add math and pure math. You're solving a log question. And the question, for example, start out with the log of x as a part of it, right? And when you solve and you solve and you solve, you get x equal negative 3, and get x equals 5. You have to say this one is not valid and eliminate it. don't it? Okay, you can't find a log of a negative number. You understand what I say? If you're solving an equation that has a log of x as a part of the equation, you give that to solve. And you solve it and you form a quadratic and you solve it and come and get two values of x. And one of the values is negative. You have to tell the examiner says this one not valid. Okay, you cannot find a log of a negative number. So anytime you solve a logs question and get your answers, you have to always check to see if the answers can work in the question because of that peculiar nature of logs. Same thing will happen in the topic of modulus functions. Or the topic of modulus functions and you solve it and you don't get the answer, you know, just take the answers as they are. Always check to see if the answers can work in the original question. Because modulus function is a peculiar kind of function. Meaning the modulus of a value cannot be negative. Right? So if your answer is going to cause if your solution is going to cause your original equation to say the log of a value is negative, you cannot accept the value that will make the log, not log, the modulus negative. And for logs, you cannot accept an answer that is saying you are finding the log of a negative number or log of 0. So you can't accept 0 and you cannot accept the negative. Understand? So when you're doing logs question and get the answer, check it back to see if it can work in the original question. Same thing with modulus. What is the topic of modulus functions? If you're doing a modulus equation and you solve it, we're going to do modulus later though. Right? Modulus functions. Or pure maths. Add maths don't get that. Just pure maths. So if you're solving a modulus equation and you get the answers, you will check to see if your answers could work in the original equation that they gave you. So that you still satisfy the definition and the properties and the characteristics of the modulus function. Same thing with logs. All right? I think we're just going to look at some typical questions with logs. So advanced and pure math students, you can get questions like this. So let me tell you now. Tell you a general rule. Students who are with me from last year should know. If you're solving an equation and the thing that you're trying to find is in the power, you take logs of both sides to get it out of the power. So if you have this, like, oh, this x is in the power right now. It says x you're trying to find. It is in the power. If you can't use an indices method and bring both sides to the same base, then to get the x out of the power, you take logs of both sides. Now when you take logs of both sides, then is when you can use the power law, which is the third one, and move it out of the power. So how do I go from this to this? By doing that same thing that I just said. This is on the slide. Let me see if it's on the slide. Let me see if it's on the slide. I'm not sure. Oh, an example is on the slide. So we can work with the example. Right? So 5 to the x equals 10. Right? 5 and 10 do have the same base, right? They do have the same base. They are multiples of each other, but they do have the same base. Right? So, because I want to get the x out of the power, I take logs of both sides and take log to the same base. Pure math students, you're going to take ln of both sides. Log to base e. You are expected to work in logs to base e at the pure math level. Right. So pure math level, when you are taking logs, pure math level, you're expected to work in log to base e, which is ln. If you are taking logs at odd math level, you are expected to work in log to base 10, lg. lg means log to base 10. I don't want to write it out. log 10. If you take logs if either of these means log to base 10. LG means log to base 10. Right, self? If you take logs and don't put up base, and write LG, it's understood to mean log to base 10. If you write LOG and don't put up base, it is understood to mean log to base 10. Pure math students who not working a log to base 10 anymore. We're working at LN. So if the question give you a base, you work to the base that they give you. But if a pure math student is solving this example, this question, they will take ln of both sides, log to base e of both sides. You're expected to take ln of both sides. That is your syllabus. Advanced students would take log to base 10 of both sides. Your answer is going to be the same. So if I'm working it for pure maths, I'm taking logs to both sides. I'm going to do ln 5 to the x equals ln 10. Because if 5 to the x equals 10, then the log of 5 to the x must equal the log of 10. The same base. This is pure maths work, ln. ln means log to base e. Then the x comes to the front. So I get x ln 5 equals ln 10. Then I'm dividing by the ln 5. So the x will be equal to ln 10 over ln 5. That's pure maths working. Very good. And you drop it in the calculator and get the answer. Add maths working now. Add maths do the same question now. You're going to take log to base 10. So add maths would go log of 5 to the x equals log of 10. LG means log to base 10. And then you take the x and bring it to the front. So you will get x log of 5 equal log of 10. And then divide by log of 5. So the x would be the log of 10 divided by the, can't write the thing. Are you a phone? Log of 5. And the calculator is going to give you the exact same answer for both of them. Get me? Remember, pure math students. So even we do a question in the class and you see me, pure math students, see me use logs. You are doing it, you use ln. Although some questions will force a base on it and work with the base that they give you. Get me? All right. This question I use logs. All right? I never get that, and the answer is 1.43. I use that one. Pure math students will use ln. 1.43, the three significant figures. Get something different? What you get? Somebody's wrote it up. Check it again. Log of 10 over log of 5. Log of 10 divided by log of 5. You don't get that? Can you calculate that? Can you calculate that? Quick. Online, everybody get that? 1.43?
Yes, sir. Yes, sir.
Statistics. Calculator doesn't start. All right, that goes in some statistics thing. I don't know what's happening here. All right, guys. Another example. So this now is actually a quadratic, using indices. Right? They're actually a quadratic. Talking about exponential equation and inequalities. That are some examples. And so this guy's quadratic equation. So you have to be able to break up using the laws of indices and realize that they can form a quadratic in 2 to the x. So remember this power of 2x right here can be split and written as 2 to the x squared. Right? You have to know those things. Right? So it becomes a quadratic in 2 to the x. Now, odd math students get this, pure math students get this and like this as well. The pure math student get this now, or the pure math student would get this, so a question looking like this, this kind of same thing. Pure math student get a question looking like this. E to the 2x plus 3 times e to the x minus 4 equals 0. That means I want to take ln, take log to this e to come down to that. If you haven't taken logs, if you come to the point of take logs. So instead of getting like 2 to the x, pure math students would have made get something like this. But then the approach is exactly the same. You understand? The approach is the same. So that is it when we break it up. It becomes a quadratic 2 to the x. So this really is the same as y squared. Other people do it this way. Y squared plus 3y minus 4 equals 0. I don't think I do that, but same thing. Right? I recognize it as a quadratic. My variable is 2 to the x. Instead of x, my variable is 2 to x instead of y. Alright, so if you feel comfortable calling it y, and proceed, no problem. Right? That's what I get. And I factorize. But can you understand that? Huh? Can you understand that? I call it y. This my 2 to the x is my variable. When I factorize it, so that this is y, so this is y, and this is y. But instead of y, I just leave it as 2 to the x. Problem. Right? And then we can proceed. We have 2 to the x equals negative 4. 2 to the x equals 1. What did we say? We said a positive number raised to a power cannot be negative, don't you? Positive number raised to a power cannot be negative. So this one is not valid. But a positive number raised to a power cannot give you a negative result. There's no value of x that will cause this to be negative 4. Positive number raised to a power cannot be negative, and the 2 is a positive number. Alright? So that is inadmissible or not valid. And so 2 to the 0 is 1, 2 to the x is 1, so x must be 0. 2 to the 0 is 1. So the answer is 0 in this question. You have a question? This line? This one? This one? I factorized. I factorized. All right. So what some persons would do, right? So this line, instead of leaving with the 2 to the x, they would write y squared plus 3y minus 4 equals 0. They are making y equal 2 to the x. But I don't want the 2 to x to confuse them. And then you factorize this, so you normally factorize a quadratic. Y, 4 and 1, plus and minus. And you will get y equals minus 4, y equals 1. But the y is 2 to the x. So you come back getting 2 to the x equals minus 4. 2 to the x equals 1. So when I do it this way, And instead of calling it y, I leave the 2 to the x as a variable. That's why I did this. A positive in 2 to the x. So you don't normally have a positive in x or a positive in y. You can have a positive in 2 to the x. So your variable, where you would normally have an x, for example, in a positive, you know, about 2 to the x. So like that, we would normally have an x here. I know about 2 to the x. Understand? The positive in 2 to the x. But if you can't see it, you can call it y. Call it 2 to the x, y as we did up here. But I would want you to practice this way so that you can grow in mathematics. Right? Grow in mathematics. Instead of a positive in x or a positive in y, it becomes a positive in 2 to the x. So my variable is 2 to the x. That's why I have 2 to the x here and here. Online, everybody online can see that as well. Students online?
Yes, sir.
All right. If you feel more comfortable calling 2 to the x, y, then no problem. Go ahead. No problem. But I wanted to practice it this way so you save some extra writing in solving the question. Right? I don't have to introduce the y. And after introduce the y, I have to go and resubstitute again at the end. All right? That's 2 examples. Next example is right here on the screen. This is now logs. Let me tell you a general rule about solving logs, anything with logs in it. So like for example, this one. You have to simplify it down and get the logs out of it. Like you can't solve the equations that is in logs with a Cartesian equation that is there. So you basically want to eliminate logs out of this one using the laws of logs. All right, what is this now? Everybody pay attention. I'm going to tell you this one time, make sure you get it. Anytime you have any logs expression to simplify or any logs equation to solve, right? You are aiming to do one of 2 things. You want to bring it down so that you can use that definition of what logism. Log of a number is equal to a 4. You can go from logs to indices to logs, right? So for example, this, you want to simplify it down to one of 2 things. Your decision. You're going to use the laws of logs to simplify it down. Right? The laws of logs that we looked at, you have to go and sit down and study and learn the laws of logs. Left to right from right to left. As you see it, you must know, you must do it. You want to bring it down to something looking like this. Log of a number to a base equal a power. Simple as that. You want to bring it down to something simple as that. When you reach there, so you therefore know that the number is equal to the base raised to the power. And then you solve this. This is your aim. Your aim is to simplify it down to this. On the left side, that is one thing you can carry down. And then you go now from the definition of the logs to that second that thing that I have underlined. And then that's what you solve. The second approach that you want to use is to get something like this. Log of to a base of a number on the left side equal log to the same base of some different number on the right side. Therefore, you can conclude that the n equals the m. And you solve this. When you're doing logs equation, logs expression, you want to simplify them, that is your objective. Either bring it down to the one on the left, remember, log to a base to a number, log of a number to a base equal a power. Therefore, the number equal base to the power, and you solve that. Or you want to bring it down so you have 1 log something on the left side equal 1 log something on the right side. So the 2 sum of them equal. And that's why you eliminate the log. Notice I've eliminated the logs out of both of them. What is that? That is what you aim to do when you're solving or simplifying log expressions. But understand that. You can note of it, screenshot it or something, write it down. That is your aim when you're solving logs equations or simplifying log expression. That is your aim. That is what you want to do. One or the other. One or the other. All right? I'm clear off the screen now. Can clear it off now? What have it? All right. That is your aim. When you're solving or simplifying any logs equation or logs expression, that is what you want to bring them down to. Especially logs equations. But to simplify them right down to that. Log of a number equal a power, so the number equal the base raised to the power. Or you can bring it down to log of something on the left side equal the log of something else on the right side. If that is the case, then the two something they must equal. And then you solve. Simplify it right down to that. That is your aim when dealing with logs equation. What you got? All right. So let's look at this equation now. Let me erase this and look at this equation. Which are these two you think it is more convenient to approach from this equation? The left one or the right one? Look at it. Which one of them you think is more convenient to approach now? The left one or the right one? Somebody online can answer to you now. This one or this one? Which one is you think is more convenient to approach right now? Huh? You say the right one? Yeah, the more approach the left one because I'm on the logs on the right side of the equation right now, just one upon it. So right now, we only have logs on the left side of the equation over here. So all I need to do is consolidate the left side and then we can use that. Using the laws of logs. So let's look at it now. I'll go to the left one, right? The first thing you want to do, move this 2. Bring it up here as a 4, right? See that? First thing you want to do is move that 2. Remember, you're trying to do is the laws of logs. So the first thing you want to do is move this 2 and bring it up here. Power law. You have to know the laws left and right. So I'm going to write the log of x minus the log of y squared equals 1. And that is a minus. So we're going to the division law now, don't it? Yeah? So this becomes the log of x over y squared equals 1, don't it? Now when it's LG is base 10, remember when it's LG is base 10, don't it? So we have brought it down to what we wanted. Log of a number to a base equals a power. So the number is equal to the base raised to the power. But when the log of a number equals 1, what's the relation between the number and the base? Log of a number to its own base equals 1. So this simply means that the x over y squared is equal to 10 to the power 1, which is still 10. I can take out the power 1 here. Right? And then from that now, this is the x equals 10y squared. And so now I'm solving these two equations simultaneously. See that? I've got the logs out of it. All right, but let's look at the slide. I think it's on the slide. Let's look at the slide. So from equation 2, I move up the power, right? See there, same thing. I apply the second law, which is the division. Then that becomes 10 to the 1. Right? If a number equals a power, so the number is equal to the base raised to the power. And I multiply that up. So x equals 10y squared. So since x equals 10y squared, I can actually take the 10y squared and substitute for the x right here. That equation, got it? What's up? See? So the second equation, you know. So the second equation, this comes from equation 2, you know. That's where it comes from, you know. So that's equation 2. So I'm saying, since I now know that x equals 10y squared, I can take the 10y squared that x is equal to and substitute the first equation for the x right here. Let's see that's what we did. More than likely. Yep. So then we get 10y cubed equals 80. What answer that? Huh? Which 10? Because LG is base 10. LG is base 10. It's not sure, but it's a base 10 right there. LG is base 10. So this becomes your N. This is your B. And this is your P. See? N, B, P. Eh? Number base 4. Base is 10. So LG means log to base 10. So they don't show it. You have to know it says base 10. If I put it on, see it is base 10, log to base 10. All right, base 10 on the LG. Log to base 10. LG 10. Log to base 10. So this 10, this number is equal to this base raised to the power 1. See here? That's it. That's where 10 comes from. But the online, okay? Online, okay?
Yes, sir.
All right? And then you solve this, right? You divide by the 10, you get y cubed equals 8. And therefore y equals 2. And if y equals 2, and put the 2 right here, so for the y. Y squared is 4, and 10 times 4 is 40. And so x equals 40. That's the answer. That's a simple example. Let's go to another one. Inequality, or try to find x. Remember, when the thing that you want is in the power, you must take logs. Pure math students are going to take ln, and math students take log to base 10. When the thing that you want is in the power, you take logs on both sides. All right? That's the first step. Take logs on both sides. I'm using logs on the slide. That's log to base 10. I'm using pure math students, you would use ln. LG means log to base 10. I'm not showing the 10, but there's a 10 there. Remember, there's a 10 there. Just like how you have ln. ln is log to base e. So ln x is log to base e of x. The base is e. The base is e. Right? So LG, we're not showing the 10, but we know it's base 10. They want to take this x using the power law and bring it to the front. The next line. See it there? Then I'm going to divide by the log of 0.2 to make x a subject, but that's an inequality. What do I have to do? Huh? If I divide by the log of 0.2, what do I have to do? I have to reverse. Equal to sign because the log of 0.2 is a negative number. See there? Know that because the log of 0.2 is negative, we must reverse the equal to sign when we divide by it. You have to know that the log of a fraction is negative. So when I divide by it and change that greater than sign to less than sign, and if you work out to the calculator, you're going to get a negative answer, negative value right there. X is less than negative 0.864. Any questions on that online? Any questions online?
No, sir.
Let's continue. Think we're going to use Friday. We're going to use Friday, 7:30 now. We started late, right? We're going to use Friday and practice some questions. So I'm about giving a classwork Friday. We want our session Saturday and do a class activity Saturday. Since we're not going to have the class activity Friday. I don't really want to spend more time on this topic. Too easy. So I'll give you some time to go and study the laws. Yeah? Huh? Yeah, I put that on the day. So what I'll do is it's on Friday. We come on Friday and we'll just practice a lot of variety of questions. Surds, logs, and indices. Right? On Friday. Instead of doing a class on Friday, we'll do it. We schedule it for Saturday instead. So get one additional day on this topic. Alright, because of the time, so I'll start to do it. I'm gonna finish it. I finished these examples. Alright, I finished these examples. It was work. Take the time between now and Friday to, in particular, learn the laws from the please. Learn the laws left to right, right to left. Right? And then you can redo some of these examples that's on the slide. Alright? There's another example. It's an inequality, but this one is not quadratic. This again is this guy's quadratic equation. We're breaking up the indices there. This can be brought to base 3 to the x. You can write this as 3 to the x. Alright? So let's go. So tell me if you see this. But tell me if you see this. However, from this to this. You have to know the laws from left to right and from right to left. So remember, 3 to the square times 3 to the x will be equal to 3 to the x plus 2. You know? Got it? So in this example, I'm coming back this way. See that? I'm going, huh? Because I have this, I realize that this right here is the same as 3 to the x times 3 squared. See that? 3 to the x times 3 squared. Right? I just put it in front, put the 3 squared in front. That's all I did. That's all I get that. Right? And then the 9 now is same as 3 squared. The 9 is same as 3 squared. That's what we have. But I'm searching for 3 to the x. I'm searching for a positive in 3 to the x. So I can switch around these two. And then write this as 9 times 3 to the x. So I get my next line. Like that. That becomes a quadratic in 3 to the x. If you want, you can do this. All right, as 2y squared minus 9y plus 4 less than 0. Now there's a quadratic inequality. I want to do quadratic inequality as a topic. Inequality as a topic. Quadratic and cubic as a topic. So when I go to worry about the factorizing and the solution of this, but more the breaking down from this to this. Right? The breaking up of the indices of the powers. To get it in that form. All right. Let me erase this because it's on the slide. So I work into the 3 to the x, no problem. So this little dot, this little dot means time. So maybe it is better to work it like this. 2 times y minus 1 times y minus 4 less than 0. That is if we write this as 2 times y squared minus 9y plus 4 less than 0. And we'll factorize it. And if you continue, you're gonna get, well actually this becomes a quadratic, a small quadratic. Alright, don't worry about this right now. Half and 4, and the less than means that you want under here. It means that the y is greater than a half less than 4. And y is 3 to the x. It means that 3 to the x is less than 4 or greater than a half. Right? But we're spending time on the quadratic, right? But to get this, you have to take logs of all sides as well. I want to still get the x out of the 4. So from there, let me show you over here. From here, what you will do next over here is take logs of all sides. So you get the log of a half is less than the log of 3 to the x is less than the log of 4. And you bring the power to the front. Bring the power to the front. So add my student now get nothing like this. So this is the log of a half less than 3 times the log of 3 times, not 3 times, x times the log of 3. X comes to the front, right? So you get x times the log of 3 less than the log of 4. And you want to find x, you divide 2 by the log of 3. And log of 3 is a positive number. So the x then will be greater than the log of a half over the log of 3 less than the log of 4 over the log of 3. And that becomes your solution. Right? If I put it back on the slide over here, you'll see. But that becomes a solution. All right? I'll repeat that through. Here, those are my rules. I want to feed them. Get the log of all sides. And put 0.5 on the slide. And then divide. That becomes the answer. I'm basically finished. What time is it? 7:40. 7:30 what? 7:28. Oh, we're not doing math. So we're back out 2 past paper. No math. We must start 5:30, you know, or later than 5:30, you know. Huh? Yeah, man, we're going to do 2 past paper, man. We're going to do 2 K past paper. Question them easy, man. Come on, what's your question them look? What's your question them look, man? Come on, one question. Come on, more math equals better. What's your question them look? K we look one to, not even C say. We look one K. Looking at a K paper for logs, I'm gonna show you them easy stuff. Right? Pure maths past paper. Let's go. Paper 2. Let's look at 2022. We have 2023. It's 2022 here, paper 2. Let's go. Keep. So if we can do the keep, we can do the admins. Don't. That's all. If we can do the keep, we can do the admins. Admins are easier. Admins is gonna be easier, man. All right, looking for a logs question. Looking for a logs question. Watch this now. It's a logs question here. Watch this now. Easy. Admins level work is soft with a capital T. Admins can get this. It's easy, you know. There's no change of base. Base 5. Base 5. Right? Base 5. Watch this now. Watch this now. Pay attention. Don't write it. Pay attention. Easy stuff. The more you solve it. Solve always means find x value. Alright? So remember, when you're solving an equation like this, what is your aim? You want to bring it down to log of a number to a base equals a power, which would then mean that the number is equal to the base raised to the power and you solve, right? Or you want to get log of a number to a base equal log of another number to a base. And then this would mean that the number equal m and then you solve, right? So which one of these this question look like we're gonna aim after? This or this? Which one? This over here, so don't it? Because we say one right there, so don't it? All right. Laws of logs now. You have to know the laws of logs. So the plus there, so when you add logs, it becomes the log of the product, don't it? See that? From the log of the product, right? So this then becomes, become fast, log the base 5 of x plus 2 times x plus 6 equals 1. Don't it? We reach this already, you know. Pure math system, we reach this already. This becomes your number. Don't it? So that number is equal to 5 raised to the power 1, don't it? And when the log of a number to a base is equal to 1, the number of the base is equal, don't it? Whichever way you want to look at it. Because 5 to the power 1 is still 5, don't it? So we know say this right now equal 5, don't it? It's a pure math side. So it means say x plus 2 times x plus 6 equals 5. So this becomes a quadratic to solve. No, they gave you log to base 5. That you find log to solve it, you know. They gave you log to base 5. Right? They gave you log to base 5. Right? So this becomes a quadratic. But remember, when you're solving a quadratic, you want to get 0 alone over set out, don't you? You can factorize it. So you have to expand this out, transpose the 5, and then proceed. What's up? Good. So I'm so much space here. No. 6 marks for that, you know. You might give a marks in a pyramid. 6 marks for this. Expand this now. X squared plus 8x plus 12 minus 5 equals 0. What I give it that? Alright, so we get the 8x. Far product and near product add to 8x. That's how we get the middle term, right? But so we get the 12. 2 times 6. What so we get the x squared? X times x. What so where this negative 5 comes from? Bring it over. So it becomes x squared plus 8x plus 7 equals 0. So the factorization, when people do add maths in a pure maths, 7. Only factor of 7 is 1 and 7. Everything positive. They don't even give you something to think. 1 and 7 equal 8. See second order quadratic and this to factorize. So that I have the maths for the easy I get to know. Think around me and tell them something I believe me, you know. I said I help you go the easier the mathematics gets. You know why? Because the question is about testing your knowledge that this equals this. The rest of it is basic stuff. Once you know, said this. Once you know the laws of logs, and you know, said this equals this. The rest of it is nothing. The rest of it is nothing, and they also know this. That's it. Two things I say you have to know, you know. Once you know them two things, then the rest of the thing, nothing in the question. You don't see a question, the amount of things you have to know to finish it. If the first line test something, second line test something, the third line test your knowledge of something, the fourth, every line testing your knowledge of something in CSEC. So once you pass CSEC, them something you know basic, they're not giving a good factorization for the, like now 6x squared minus 15x plus 7 or 17 for factorize, or 15. So what them give people in a CSEC for factorize? That them again a CSEC for factorize. I mean put on 7 years so or 11. Honestly, because they're testing your ability to factorize. They're not testing your ability to factorize yourself. They might test if you know this and this. Once you show say you know them, the rest of it easy. You get me? You know how to factorize. I'm telling you, the higher up you go, the easier the mathematics get. Once you learn the basic things. But this now is just x and x, 1 and 7, everything positive. So you get x equal -1, x equal -7. However, I put it up. What we have to do now? We get x equal negative 1 and x equal negative 7. What we have to do with the answers? You have to make sure that the answers can work in the original equation. If I plug in the negative 7, look right now. These are different color. If I use the negative 7 right here, I'll be calculating the log of negative 1, which you cannot find the log of a negative number, don't it? See, if I use the negative 7 here, I will calculate the log of negative 5, don't it? So you cannot accept negative 7 as an answer. It is not a valid answer based on the question that was given. And if you try the negative 1, you're good to go. Because if you put it here, so you find the log of 5, don't it? And put it here, so you find the log of 1, don't it? So you cannot accept this answer. This is not a valid answer. And this is your answer. Now what we know? If CXC, you are the CXC, now recognize. So this is not a valid answer. And still have to give you a marks because you put it there. Because you are showing an advanced knowledge by saying you cannot accept an answer that will result in the original equation being inadmissible. You get me? So you have to eliminate the don't cross it out, just write not valid and put this as the answer. But that's not. But that's a pure maths question. Easy as that. So let's find another one that was 2022. More maths equals better maths. Let's try 2021. We're working until about 5 minutes to 8, man. I'm not lazy, so man. We started late. We started late. But we don't look at work. All right. It is being recorded. You have to leave. That's not an easy one. So I change of base here now. Change of base. So add maths learn some. That's a change of base question. So the base them different look. So you have to change the base. So the base different. You bring everything to the same base. See that? You have to bring everything to the same base. What base would we bring everything to? Base 2. Right? Bring everything to base 2. So this is a question now you would not get an add maths. But there's nothing to it. If you know the change of base law. So I bring everything to base 2. So watch this now. So pure math students would get this. Add math students would get this. Alright? So watch this now. I'm going to leave this as it is. And which one do you think we are trying to get? We are trying to get it down to log of a number to a base equal a power, don't it? So we have a number here, so we're not trouble, right? That's going to be our number, don't it? That's going to be our P. We're going to leave it as our P. So we'll take this side and consolidate it down to something like this. And we're using 2 as the base. 2. Good? All right, let's go. The first thing I want to do is change the base. So this one stays as it is because it is already base 2, right? So it becomes log to base 2 of x. This now, remember, it becomes log of x over log of 4, right? And then put the 2 of them to base 2, right? So this becomes log of x over log of 4. Put the 2 of them to base 2. Then this one, same thing. It becomes log of x over log of 16. Put the 2 of them to base 2. And this equals 7. It's gonna get easy now. Because this can be worked out. That equals 2, you know. Let's put it in the calculator. And this equals 4. I'm gonna say it equals 4. I'm sure I'm gonna say it equals 4. See that 16 here? It is the same as 2 to the 4th power. Let me write the next one. Let me leave this as it is. This becomes log to base 2 of x plus log to base 2 of x over the 4 here, same as 2 squared. It becomes log to base 2 of 2 squared plus log to base 2 of x over log to base 2 of 2 to the 4th power equals 7. But I write it down. This 2 will come to the front, and this 4 will come to the front. See that? Good. And when it comes to the front, what will happen is that the log 2 of this 2 stays 2, don't it? Comes 1, sorry. And then this also is 1, right? So you can see that this is going to work out to be 2, and this is going to work out to be 4. But I can see that. But let me write it out for the purpose of the class. Log to base 2 of x plus log to base 2 of x over 2 times log to base 2 of 2 plus log to base 2 of x over 4 times log to base 2 of 2 equals 7. So this is equal to 1. I'm going to circle it. This is 1. And this is 1. So that denominator becomes 2. That denominator becomes 4. Look what you actually have. Look what you actually have. Watch this now. You have log to base 2 of x plus half log to base 2 of x. I'm dividing this by 2, don't it? Plus a quarter log to base 2 of x equals 7. So because I add them a multiple of log to base 2 of x, I can add them up. It's really 1 plus a half plus a quarter, don't it? Put another way, watch this. Put another way. I can write this as 4 over 4. Write this as 2 over 4. And this stays as 1 over 4, don't it? I'm going to add them again. 4 plus 2 is 6 and 1 is 7. So I get 7 over 4, don't it? So reduce this to 7 over 4 log to base 2 of x equals 7. And the 7 them cancel, don't it? 7 and a 7 cancel each other, don't. When they cancel each other, we'll multiply with 4. So I end up get log to base 2 of x equals 4. 7 is cancel, right? And then this x is now this 2 raised to the power 4. See? Number equal base raised to 4. So the x is equal to base 2 raised to the power 4. 2 to the 4 is what? 16. X is 16. Let's do that. Much marks I need for this? Marks I get. I realize these are all the same. Look, I realize that these are all the same. So there's a sum of this. There's one of this, there's half of this, there's a quarter of that. And the half is same as 2 over 4, and then a quarter. And the 1 is same as 4 over 4. So let's add up all of these, the numerator. 4 plus 2 plus 1 makes 7. 7 over 4. Get me? 7 over 4.
So can you say that again, please? Can you say that again, please? Like how you got all the fractions in front?
Say it again.
Yes, please.
All right, let's go through it again. From about here, right? I want to do all the way up. All of it?
Nah, not all of it.
From here?
Yeah.
All right. So you understand this, we replace this with a 4 for the 4. We replace the 62 to the 4th power, right? We're searching for the log to base 2 of 2. That's why we do that. So this 2 will come to the front using that power law of logs. And this 4 will also come to the front using the power law of logs, right? So I'm going to write log to base 2 of x, which is what this is, plus log to base 2 of x over 2 times log to base 2 of 2. So that this and I bring it to the front, that's why I get that 2 there. And then this 4, I'm going to bring it to the front as well, using that law. I get plus log to base 2 of x over 4 times log to base 2 of 2 equals 7. But the thing is, that the log to the base 2 of 2 right here is equal to 1. And the log to the base 2 of 2 right here also is equal to 1. So under the denominator, you say just a 2, and the denominator, you say just a 4. So because we divide them by a 2, this is really half of this. Because we divide them by a 4, it's just a quarter of this. So this can therefore be written as log to the base 2 of x plus half of this. Half of log to the base 2 of x. Why am I doing that? Because I realize that all the terms have the same thing in them. Just some of those. 1 plus a half plus a quarter of the same thing. And then a plus a quarter of log to the base 2 of x. And that is equal to 7. If you add up the 1 plus the half plus the quarter with the calculator, it becomes 7. Because I can put a 1 in front of this. So the 1 plus a half plus a quarter becomes 7 over 4. 1 plus a half plus a quarter is the same as 4 over 4 plus 2 over 4 plus 1 over 4, which becomes 7 over 4. So all of this becomes 7 over 4 log to the base 2 of x. I'm going to write that. So I get 7 over 4 log to the base 2 of x equals 7. The first thing that will happen is that we need to multiply this away over here. So that we multiply the 4 and divide under the 7. Or we can look at it and say, the 7s on both sides cancel. This 7 cancel, give me 1 and give me 1 there. I take this 4 and I multiply it up. Any way you want to look at it. Any way you want to look at it. The result is the same. So I can look at it another way and say log the base 2 of x equals, I'm going to put the 7. This 7 that was there before times 4 over 7, which the 7's cancel and gives me 4. So I now have log the base 2 of x equals 4. So using the same law of logs, this is a number is equal to this base raised to that power. So the number x is equal to the base 2 raised to this power 4. Because log of a number is always equal to a power. This is a power. And the 4 is a power. So that's what we get. And then this now is equal to 60. Understand it better now?
Yes, sir.
All right. 2021. Let's look at 2020, 2019, because there's no exam in 2020. 2019. More maths equals better maths. Let's go. Now there's no logs on this one. No logs on this one. No logs on this one. But we have this. This is it's an indices. So we can do this one. We can do this one. We can do that one. We're doing Surds, logs, and indices, so we can do this one. So this one looks like it can become a quadratic in 9 to the x, don't it? See that? Can become a quadratic in 9 to the x. See it? Don't it? So what is 81 to the x equal to? 81 to the x is the same as 9 squared to the x, which is the same as 9 to the x all squared, don't it? What I do with that? I'm going to replace this with 9 to the x all squared. Ready now? So I'm going to equation is going to become. Let me shift this over. Shift this over. Sorry. Put this over here, so that's where it comes from. Multiply by the 9 to the x. And the quadratic in 9 to the x. Watch this, watch this. So first I'm gonna write it as 3 minus 4 over 9 to the x minus 4 over 9 to the x squared equals 0. I want to form a quadratic in 9 to the x. What do you think I'm going to do with this equation now? To get a quadratic, I want to come out like one quadratic, like y squared plus something y plus a number equals. Huh? Yeah, get rid of the fraction. Oh, they might get rid of the fraction. What do I do with this? Quarter. No, man, 4 is a problem, man. You want to get them from under the denominator, so don't want them under there. So I'm going to multiply by 9 to the x squared. If I multiply by 9 to the x squared, I won't have any fractions left. See that? If I multiply by 9 to the x squared, I won't have any fraction left. Multiply by 9 to the x all squared. That's what I'm going to do. When I multiply by 9 to the x all squared, this becomes 3 times 9 to the x all squared. 3 times 9 to the x all squared. This becomes 4 times 9 to the x alone. And this becomes minus 4 equals 0. See that? The quadratic. Now, if you want, you can call this y and call this y. If you want, let's do it that way. We have before it. We have progress before perfection. So we could call this y and call this y. So this becomes an equation 3y squared minus 4y minus 4 equals 0. Good? So we'll factorize this now. Remember now, the y equals 9 to the x now. Right? That's what we did now. We put in y equals 9 to the x. That's what we did. That's what we did, right? So y equals 9 to the x. So we're going to factorize this now. It becomes a quadratic in 9 to the x. It becomes 3y and y. And then no more 4 right there, so we need 2 and 2. 2 and 2. Why? Because 3 times 3 is 6. 6 minus 2 give me 4. See that? So this tells me that two signs in the bracket are different. 1 plus and 1 minus. Do the larger product, the minus sign. This product is 6 times. This product is 2. Make the larger one negative. So make this one negative, the larger one negative, and the smaller one positive. Good? So we end up getting now y equals minus 2 over 3 or y equals 2. Remember, so y equals 9 to the x, you know. I can go back and put now 9 to the x equal minus 2 over 3 or 9 to the x equals 2. Which are them valid? A positive number raised to a power cannot be negative. Let's say anyone knows that is true. You don't want to log both sides to get x out of the power, don't you? Don't it? Let's say they know that a positive number raised to a power cannot be negative. Then to get the x out of the power, you don't want to take logs on both sides. But you can't find the log of a negative number. They still can't move forward. See? They can't find the log of a negative number. So anyway you look at it, this is not valid. This one is not valid. Not valid. Can't solve. So we really want to solve in this. So we solve this now. We want to get x out of the power. What do we do? Take logs on both sides. Pure math students doing this paper, they have to take ln of both sides. So you do ln 9 to the x equals ln 2. Add math students will just write lg instead. For log. Log to base 10. Then this power comes to the front. So it becomes x ln 9 equals ln 2. They divide by the ln 9. x equals ln 2 over ln 9, and I work to the character. I can leave this as the answer. It won't penalize if you leave that as the answer. See there? If you leave this as the answer, it is still correct. If you could work to the character and put decimals. If you want to give an exact answer, you give them that. ln 2 over ln 9. And so because ln 2 over ln 9, it actually can become this thing. Now, watch this now. It can become, watch this now. Laws of log. Can become log of 2 to base 9. But that's don't it? I think I'm going the other way, not that way. I think I'm going this way. And this equals this by the change of this. See that? I can actually leave this as my answer. This one. But I can leave this, or I can use that. Same thing. So guys, I'm charging you. I'm gonna end it now. I'm charging you, everybody here and online. Learn the laws of logs. Learn the laws of indices from the summary page. All of them, they will make the questions easier to do. You can't do indices question and logs question unless you learn the laws first. You have to know the laws from left to right and from right to left. But I will stop if you don't learn the laws. It doesn't make sense. You have to learn the laws inside out, left to right, right to left. So as you see a question, you know which law to apply. You know how to manipulate and simplify and rearrange. You have to learn the laws. The questions are about application of the laws. So you have to learn the laws. All right? I'm going to stop it here. Friday, we're going to practice questions. I'll give you a classwork on Saturday. Okay, everybody? All right. Bye, people online. Hi, Alex and Shadi.
Bye, Sue.
Bye.
All right. All right. Bye. Alexi. All right.